Internet. We meet again. Hello. So, this week is all about complex systems and systems thinking. And the question we're going to start with today, or the thought, is you're never right, you're only a little less wrong. And the inspiration for this week's endeavor, the wandering of this week, was actually from a series of books I've just finished from Nassim Taleb. And there's a lot of points made in the series of books, but there's one that kind of a common thread throughout, which is basically everything is uncertain, nothing is certain, we don't really understand the majority of the world around us. And that spurred my interest in understanding more about complex systems and themselves and complexity. And I wanted to know what that is, what it meant, how it kind of intertwined into all these different areas of research for engineering and biology and astronomy and physics and all these different areas. But I actually came across an idea of systems thinking. So I wanted to research into that a bit and see if there's anything I could take away from those learnings and apply to my own life going forward. And that's kind of what I wanted to share with you here today, as well as in the post that I've written. So please go look at the post. If you don't want to read the whole thing, just skim it. And if you don't want to skim it, just go to the very end, because there's a point that I came across which really resonated with me. And I think near the end where it talks about being bigger is not always better, I think that's the most important piece of the post. So go see that. All right. So in this video, we're going to talk about a few things. As usual, we're not going to go through the entire post, but we'll talk about what a system is, what makes it complex, what is systems thinking, where did it come from, and some lessons I learned from this. Let's first start with what is a system. So in general, a system is like a metamorphous bubble. And I'm going to put an image somewhere so this is helpful. And imagine there's a boundary around this system, and there's an input and output, and then there's a wider environment around it. So this could be almost anything, and within this system there's going to be a bunch of stuff going on, and there's going to be some sort of something that comes out of it. It's very abstract. Let me kind of bring it to an example that makes it more concrete. So think about the ecosystem of the planet that we live in today. And within that ecosystem there are smaller subset ecosystems. So for instance, if you have a garden, and in that garden you have soil and water and sunlight, etc., there's all these different parts that are working interconnectedly together to produce some sort of outcome in that garden. And that garden could be potatoes, that could be bananas and apples, whatever. In that garden you're trying to produce something, and to do that, that system has to have a lot of stuff going on inside of it. A lot of inputs and some output. That's a general example of a system. And systems are all around us. And the majority of the systems that are around us, which I found out through this research, are complex. There are very few simple systems that we ourselves can truly model, understand, and predict. A very simple system that I thought of was basically a clock. We know how a clock is made, we know how to take a clock apart, we know what each piece does, and we can predict what the clock's going to do 2 hours from now. It's going to tell time. But some examples of systems all around us, like I said, the planet is a massive complex system. There's financial markets. So those financial markets are systems in themselves, and they act chaotically. There's social systems, social dynamics. So I have my neighbors. We interact with each other. Then I have the city I live in. Then I have the country I live in. Then I have the planet I live on. And all of those different social systems have different social dynamics. And then there's the internet. So the internet has a bunch of computers interacting with each other, and that's a system in itself. So there's an endless amount of systems. Our body is a system. I wouldn't be here if there wasn't a super duper complex system with subsystems working perfectly. So it's just an endless list of fascinating places where there are systems, which are complex. So my next point is to kind of define what makes a system complex, because there's simple systems and there's complex systems. So the definition of a complex system is debated amongst many different kind of system thinking gurus, and there's no definite definition, but there are three common themes throughout each of the definitions that I want to touch on here. So the first theme is adaptability. So that system is able to adapt over time to its surrounding environment. So if something happens to it, it can adjust. And for instance, let's think about an example of, we'll go back to humans. So we humans have adapted to the system around us, and we've built tools to kind of help us out. But for instance, our body biologically adapts. So think of how our temperature within our body usually stays between, I think it's like 97 and 98 degrees Fahrenheit. And that adjusts over time because your body basically burns energy to keep you warm, and it does some other funky stuff to make you sweat and do other things to make you cool. And that's basically an adaptable system that's continually adjusting itself to its surrounding environment. So adaptation, being able to adapt. The next one is interaction. And interaction in the sense that there's more interactions within the system than there are elements within the system. Let me explain that. So there's a system, and in the system, imagine a bunch of little circles, and all those little circles have lines connecting each other. So imagine each circle being a component of the system. So you can take that circle out and you can examine it and look at it, and then you can put it back in the system. That's a component of a system. But the issue with systems is that if you take that circle out of the system, you disrupt all the connections that were touching that circle, so all the lines. And a highly complex system tends to have, double, triple, quadruple the amount of connections to the different components than the components themselves. So there's hundreds and thousands and millions of connections, and then maybe a couple hundred components. So kind of picture that. And an interesting example I came across in some part of a book that I was reading for complex systems is that if you want to examine a cow, you have to kind of examine it in different ways. So you can break the cow into its different pieces and see what the different parts of the cow do. But in the end, you would only understand so much of what the cow is doing. But if you want to understand the complexity of the cow and understand how it interacts within itself and how the system functions, then you have to examine the cow as it's alive instead of breaking it into pieces. So you can't cut a cow in half, and you don't get two cows after doing that. So the complexity piece is interesting because you want to watch the interactions between the components and not the components in themselves. So interactions over components. And the last one is going to be emergence. So funny word, but basically the premise of emergence is that if you have two individual things, these two individual things have behaviors, they have attributes, so they do things on their own. But when you take these two things and you combine them, then what happens here is they start to have new behaviors and new different types of actions and attributes when they're combined. And what those combined interactions are emergent. So those are emergent properties from two different individual components. So a complex system tends to have the ability to adapt over time. It tends to have a lot of interactions over components, and then it also tends to have some sort of emergent behavior based off the two separate components. That's generally how they define complexity within a system. They meaning the theoretical gurus of systems thinking. I've mentioned systems thinking, and I've mentioned complex systems. So let's talk about systems thinking and what really is that thing, and how do people approach this process. When you look at how we have been educated and raised historically throughout our traditional educational systems, the majority of the processes that we used when we approached a problem is based off this thing called reductionism or reductive approaches. And it's super useful. It's helped us get through a lot of stuff within science, and it's something that we should continue to use. And the way that it works is that reductionism or reductive kind of approach is when you reduce something down to its component parts. So if I wanted to know more about how this phone worked, I would take the phone apart and I would look at the individual pieces of the phone to see how they functioned, and then I would put it back together, and then I would have a phone that functions, right? So reductionism is breaking it down. Now there's another sphere of approaches, and there's another sphere of approaching problems, which is called, it's a holistic approach. And this holistic approach, instead of breaking the pieces down of a system and looking at the different pieces, you actually look at the system more holistically, and you look at the interactions between the pieces instead of the pieces by themselves. So you're not necessarily focusing on the components, you're focusing on the functions of the system, what it's doing, and you're also focusing on the interactions between different pieces. So if I poke this, then something happens here. if I touch that, then something happens here. And you're kind of looking at the in-between space of the system instead of the components. So it's a more holistic view. And there's a lot that can be said about systems thinking, about how people use it, how they approach it, how they speak about it. And you could rant about it forever, and I'm not going to do that. But instead, I just wanted to show or explain 3 different lessons I've taken away from this that I thought were quite interesting and could be interesting for you. And there's more in the post that I've written, but for video purposes and for kind of being concise, we'll stick with 3. The first one I'm going to speak about is the importance of interaction over prediction. And this was kind of a combination between a talk that I've recently watched by a guy named Dave Snowden, I think. I'll put a kind of a video clip here.
You understand a complex system by interacting with it, not by analyzing it or modeling it. I'll repeat that because it's key. You can't understand a complex adaptive system through modeling or analysis. You can only understand it by interaction with real-time feedback loops over multiple agents, so you don't get cognitive bias. And this is kind of like 101 science.
And there's also a conversation through Nassim's books as well. And the premise of this is basically that we humans like to predict. We like to kind of forecast into the future to either protect ourselves or benefit ourselves in some way. And most of the time, if not all the time, that usually fails, or it's usually pretty wrong. And their approach here and the way that they discuss this is prediction's okay for certain things, but most things it's not. And the next best thing you could do would be interaction. And interaction in the sense that if you don't necessarily know how to predict something and you don't know what the single outcome is going to be, you interact with the system that you're in and do it in different ways and experiment with each one. So say you're trying to figure out how to make a decision for a government, and the government wants to make a decision and they don't necessarily want to have negative consequences on the citizens of their government or of their country. So instead of just rolling out a different policy and saying this is what we're going to do, they can kind of experiment potentially, where they could say, okay, we'll have this policy, we'll slightly adjust the policy and do it this way and this way and this way, and then you'll have maybe 10 different kind of cohorts of people that receive this policy over a short period of time. And you're interacting with the system to see what are the potential negative consequences of doing these different types of things and testing them and seeing how it's going to work out. And that's the interaction piece. So you're interacting slightly different ways with the system to see how it unfolds. So interaction over prediction is the first one, which I thought was quite interesting. Next is a humbling one, which is basically to accept ignorance. And to accept it in a way that you're not necessarily kind of bringing yourself down, but you're accepting the fact that the majority of the world is too complex for our minds to understand at this moment in time. So be content and humbled with the fact that you're probably ignorant with most situations and most outcomes. And that ignorance comes honestly with a sense of, for me, freedom. Because most people you speak with in a lot of companies and businesses and interact with whom wherever, they tend to be quite certain about their decisions, and they tend to be quite certain about the information that they understand and know. And in the end, like I said in the beginning of this post, you're not right, you're only a little less wrong. And having that ability to kind of sit in the transition state, the liminal state, not necessarily saying something's black or white, but it's gray. Everything is gray, and it's on a spectrum. And kind of thinking about that and internalizing it and realizing that it's okay to not be always definite right, because most people aren't. And that kind of gives you the freedom to be able to change your opinion and also change the information in your head and your perspective on certain things, and you're not always kind of secluded or set off into one area or one decision or idea. So accepting ignorance was another one. This last one was really interesting and something I really liked and I appreciated a lot, which is bigger isn't always better. And this comes in many different facets. And I actually got this idea from both Nassim's book series, and there was a talk that I've recently watched and related to systems thinking, which the general idea is that most companies die. That's basically it. Most companies die off. And what happens with a company is they go through this kind of conundrum of explore and exploit, and it's just the nature of capitalism, and it's the nature of trying to sell a product or a service to a group of people, where you explore multiple areas to basically figure out, okay, what's the service or product or thing that we're going to provide to society, and we're going to sell it to them and benefit them in some way. Going through this process, you're kind of iterating and you're exploring with these different things to see which one works the best. Once you figure out which one works the best, then you exploit that one as hard as you can and scale it up. So as you're exploiting this and you're scaling it, the company over time starts to specialize in this specific thing that it's doing. And when specializing in this area, then it loses its ability to explore other areas because it's exploiting this one and scaling to a point where it's kind of reaching maximum capacity. And you'll see when researching complex systems that there is always a maximum, or there's a point where basically something hits a limit and then it drops drastically. And with most companies, if you look historically, all these companies have exploited a product or a service or an area, and then it gets to a point where it's time to, die off, and it goes and it disappears. And this actually isn't just in companies, but it's in biology, it's in ecosystems, it's in different types of animals and insects, where they emphasize the point in these systems that it's actually sometimes better to be small, nimble, and loosely coupled than it is to be certain, large, and dependent. So I took away from this an interesting concept and idea for my own life that I've always, not always, but I've been kind of in the realm of doing for the past year or so. It's something I want to double down on, which is being small in the sense of the amount of cost in my life. So minimizing the amount of cost on all the things I have around me, minimizing the amount of stuff that I have, minimizing the amount of dependence I have on a single entity or company that I work with or for. And it's basically trying to reduce and be as small as possible, but also be as kind of loosely coupled, where you can be jostled by the environment around you, you can be impacted by it and moved, but you're not necessarily going to be impacted to the point where everything implodes and explodes and you just have this drastic, horrible situation that happens. So the moral of this one is small is actually better in most cases, at least in my head right now. It might change some other time, but after going through this process, I'm kind of convinced that smaller is actually better than bigger. With all that being said, this was an interesting week and I enjoyed it. I hope that you enjoyed this video, and I hope that you enjoyed the post, not the podcast. And let me know if you have any questions around this idea, or if you have any suggestions for future ideas. If you want to subscribe to the newsletter, do that. Yeah. And I will see you, Internet, next week. Mwah.